Hi students, welcome to the session. I am Dr. K. Varada Rajkumar, Associate Professor, Department of CSC, AIML, MLR Institute of Technology, Hyderabad. In our previous classes, we learned about different types of searching trees. In this session, we will learn about the comparison of these search trees. Overview of the presentation. In this presentation, so first we see what is search tree. So after that, we discuss about different search trees with definitions and pros and cons. And finally, we compare all these searching trees. Outcome of this lecture, at the end of this lecture, you all are understand various searching trees including binary search tree, AVL tree, B trees, red black trees and split trees. And you select most suitable search tree based on specific requirements and performance considerations. So what is search tree? A search tree is a data structure that organizes elements in a hierarchical order. So hierarchical order means, so this follows tree structure. So this is the hierarchical order. What is a search tree? A search tree is a data structure that organizes the elements in a hierarchical order, allowing for efficient insertion, deletion and search operations, so based on unique key associated with each element. Here, so for example, this is the 50, here 25, 60. Now, if I want to insert 70, 70 is greater than 50. So, we traverse to right side. 70 is greater than 60. So, again traverse to right side. Here, we are going to insert 70. Okay. Search trees are fundamental in various computer applications, providing efficient data management and retrieval. So, data management is nothing but a insertion, deletion and searching operations. Now, we will see different types of searching trees. One is binary search tree, AVL tree, B tree, red black tree and split trees. Already we discussed in detail about all these trees in our previous classes. So now we see what are the pros and what are the cons of these trees. So first one is binary search tree. Binary search tree. Definition of binary search tree. So BST is a tree data structure where each node has at most two children, referred to as the left child and right child. Now this is the example of binary search tree. Here, so this part is left child of 8. So this part is right child of 8. The left child contains only nodes with keys less than the nodes key. Here node is 8. If you observe, all the left side values are less than 8. The right child contains only nodes with keys greater than the nodes key. If you compare here, in right child, all the nodes are greater than 8 here. So now coming to pros and cons. So what is the pros? So pros is simple implementation and intuitive structure. It is easy to understand and easy to implement. Now, efficient for operations with average time complexity of big O of log n for balanced trees. So now here if you observe this diagram, so now 8 is the root now, 3 is the left child of 8, so 10 is the right child of 8. So it is balanced tree. Okay. Now coming to cons of this binary search tree, so potentially unbalanced. So leading to worst case time complexity of big O of n if the tree degenerates into a linked list. So for example, consider, so these are the values 10, 20, 30, 40, 50, 60, 70. Now what is the root here? 10 is the root. So 10 is a root. Next 20. So 20 is greater than 10. So 20 is right child of 10. Next 30. So 30 is greater than 20. So 30 is right child of 20. So 40. So 40 is right child of 30. 50. 50 is right child of 40. 60. 60 is right child of 50. And 70 is right child of 70. If you observe, it seems to be linked list only. Starting node is 10 and last node is 70. Now in this case, to access 70, the time complexity is big of n. So that is a disadvantage we have in binary search tree. Okay. So next tree type is AVL tree. So AVL tree is also a type of binary search tree that maintains its balance using rotation. It is named after its inventors Adelson, Elsky and Landis. So this is the AVL tree. So these are the inventors. In an AVL tree, the height of the two child subtrees of any node differ by at most one. At most one. Insert or delete the element from AVL tree. You check the tree is balanced or not. So balanced or not means the difference between left subtree and right subtree at most 1. At most 1 means it may be minus 1, 0, plus 1. Okay. If at any time during insertion or deletion, so this property is violated, the tree is rebalanced using rotations. So coming to pros and cons. Here, pros. So guaranteed big of log n height ensures efficient search, insertions and deletions operation. Prevents the tree from becoming unbalanced and degenerating into a linked list. So for example here, same 10, 20, 30. In binary search tree, how we can insert 10, 20, 30. Okay. Now in AVL tree, so 10, next 20. So 20 is greater than 10 and it is balanced. When we insert 30, it is unbalanced. Why? The height of right subtree is 2. Left subtree is 0. 0 minus 2 equals to minus 2. So it is unbalanced. Always the values between either minus 1 or 0 or plus 1. But here it is minus 2. So what we are going to do? We do some rotations. Okay. Now how we can balance this? Rotate to left side. So it becomes as 20, 10 and 30. Now it is balanced. Okay. Now coming to cons. More complex rotations compared to standard PST. Here we apply some rotations and requiring additional computation and restructuring during the insertion and deletion operation. If it is a binary search tree, it is very simple to insert the data. But if it is a AVL tree, when we insert or delete the data, again you are going to check one factor, that is balance. If it is unbalanced, then rotation. So for this we do some additional computations. So that is a cons of AVL tree. So next searching tree is B tree. A B tree is a self-balancing tree data structure that generalizes the binary search tree by allowing more than 2 children per node. Now up to now, so this is the tree. Okay. Coming to binary search tree, we can accommodate more than one value in a node. For example, 5, 10, 15, we insert in one node. So that is a B tree. It is designed to work well on systems that read and write large blocks of data. If you have large blocks of data, then we select B tree. So B tree maintain balance by ensuring that all leaf nodes are at the same depth. So this result in a balanced tree with minimizing height, suitable for efficient multi-level indexing. Here the all leaf nodes are at the same depth. Okay, that means here we are going to maintain same depth. So now already we discussed in detail about B trees in our previous lectures. And coming to these are the properties, order of M and height. The order of M of B tree defines the maximum number of children a node can have. So for example here, so these are the 3. So the children are 4. So less than 5 values are 1 children. Now values between 5 and 10 we store in second children. Values between 10 to 15 we store in third children, and greater than 15 we store in fourth children. So that we call as a M. The order of M of B tree defines the maximum number of children a node can have. If it holds 3 values, then M equals to 4. If the number of values is 4, then M equals to 5. So already we discussed in detail in our previous classes. The height of B tree is logarithmic related to the number of keys, ensuring efficient search, insertion and deletion operation. Why? Because the B tree is also a binary search tree. Now coming to pros and cons. So pros are efficient disk access due to minimized height and large node sizes, reducing the number of disk reads and writes. Now here for example, this is the node. In this node, if I store 5 values, so 10, 20, 30, 40, 50. If it is a binary search tree, then 10, 20, 30, 40, 50. Now to access this 50, we can traverse all these nodes. But here we store all 5 keys in one node. When it loads into the primary memory, we can access 50 directly. So that is the advantage of B tree. Suitable for databases and file systems where large blocks of data are read or written at once. So cons. More complex implementation comparing to simple search trees. You understand that if we compare these B tree with search trees, binary search tree or AVL tree, the implementation is complex. Higher memory usage due to storage of multiple keys and child pointers per node. Here the this node contains 5 keys, so the children are 6. So next tree is red black tree. So red black tree is a type of binary search tree with additional properties to maintain balance. In AVL tree, how we can balance? The balancing factor is either -1, 0, +1. Okay, here also using some properties we maintain that balance. It ensures that the tree remains balanced with a set of rules governing node colors and tree structure. Here we are using 2 colors. One is red, another one is black to maintain this balance. So red black tree properties. Each node is either red or black in color. The root is always black. All leaves, nil nodes are black. Red nodes cannot have red children. No 2 red nodes can be adjacent. Every path from a node to its descendant nil nodes has the same number of black nodes. So what it is? For example, this is the 10. So always the root node is black in color. Okay. So now all leaves nil nodes are black. Now 10 is the root. This have left child and right child is null. Now this we represent as black. Already we discussed in detail in our previous classes. Red nodes cannot have red children. For example, if I insert 20 here, so now 10 is black, 20 is in red. Now if I insert 30, it is red, so the property is violated. What is the property? Red nodes cannot have red children. Now in every path from a node to its descendant nil nodes has the same number of black nodes. So coming to pros and cons. Pros: provides a balanced tree structure with simpler rotations and color changes compared to AVL tree. In AVL tree we apply rotations. In red black tree you apply rotations, or you can change the color to balance the tree. Cons: so slightly less balanced than AVL trees, which may lead to slightly less efficient operations in practice, though still guaranteed to the logarithmic. So here, so for example, if we insert the 10 here, so 10 is root now, it is in black color. So 20 is red, yes, it is in black color. Next 30. Now red, red. So you can change the color here. Now if you observe here, so this is the red black tree, but if it is AVL tree, you are going to rotate and maintain the balance. So when comparing to AVL trees, the red black trees which may lead to slightly less efficient operations in practice. Next tree is splay trees. A splay tree is a self-balancing binary search tree. It is also a binary search tree. So recently inserted or accessed element become as a root of the tree by performing a sequence of rotations called splaying. Here the rotations we called as a splaying. Now what is a splay tree? Splay tree means newly inserted data or recently accessed data is become as root here. Okay, to make this we can do some rotations. So this process we called as a splay. Okay, splay trees are particularly effective for catching scenarios where frequently accessed item should be so quick to access again. That means repeatedly you are using a particular data element that I want to store in a cache memory. Now in these places I am going to use splay trees. Okay, so coming to pros, on average the time complexity for operations like insertion, deletion and search is big O of log n. Elements that are accessed frequently are kept near to the root, improving the cache performance. Coming to cons, in the worst case, individual operations could take as long as the size of the data big O of n. However, on average, so things are usually faster because of how the operations are spread out over time. Now, every time you are using a different data item in the tree, then the accessing time becomes as big O of n here. Okay, so these are the pros and cons of splay trees. Now we compare all these search trees. So what we discussed up to now? We discussed about binary search tree, we discussed about AVL tree, we discussed about red black tree, B tree and split tree. Now we see the time comparison of all these searching trees. In every searching trees we have three operations. One is insertion, second one deletion, so third one searching time. Okay, now for binary search tree, it is big O of h. H represents height of the tree. So the deletion time is also big O of h. The searching time also big O of h. So space complexity is big O of n here. Now balancing mechanism is there in binary search tree? No, no automatic balancing is available in binary search tree. So coming to use cases, it is simple general purpose search operations. Now AVL tree, the insertion time is big O of log n. Coming to deletion, big O of log n. Coming to search time, big O of log n. And space complexity is big O of n. Now is there we provide any balancing mechanism in AVL tree? Yes, it is self-balancing. Height is balanced. If the height is greater than -1, 0 or 1, then we apply some rotations. So use cases, use where frequent insertions and deletions are needed. So red black trees, the insertion time is big O of log n, deletion time is big O of log n, searching time is big O of log n and space complexity is big O of n. Here it is also self-balancing. How you are balancing the tree? By using colors. Okay, so use cases, balanced performance for search, insert and delete. Next, B tree. So B tree, insertion time big O of log n, deletion time big O of log n, search time big O of log n, space complexity it takes so big O of n. Here we are using balancing mechanism or not? Yes, balanced using multiple keys per node. So use cases, database indexing and file systems. Splay tree. Splay tree insertion time, big O of log n. Deletion time, big O of log n. Searching time, big O of log n. And space complexity is big O of n. It is also self-adjusting. Here, newly inserted data or recently accessed data is become as a root here. So here use cases are to frequently accessed elements are quickly accessible. So this is about the comparison of different searching trees. Now coming to summary of this session. In this session, we discussed about different data structures. So these data structures have varying time complexities for operations like insertion, deletion and searching. So self-balancing trees, AVL, red, black and B trees ensure efficient operations by maintaining balanced structures, and selecting the right data structure ensures that operations are performed efficiently, optimizing performance and resource usage. What it means? So for example, you are defining one database. In the database, you want to access frequent data. Then you select split tree. You have more number of data elements in database. Then you select P tree. Now I want to maintain the balance of the tree. Then you select AVL tree. No, I don't need to maintain any balancing. Then you use binary search tree. So based on your requirement, you select a particular search tree. If you have any doubts, so place your doubts in the comment section. I will try to answer all your questions. In next class, we will start graphs. Thank you.